Okay, in this video what I'm going to do is record some information about the review chapter. So as you'll note on the syllabus, and if you have the textbook, there's one chapter in the book that's abbreviated as review, or just with the letter R. And in this chapter, it's covering a lot of things that you should have ideally learned in high school or in previous courses. Nothing that is too terribly complicated, but things that we expect you to have a baseline knowledge of in this course. So if you're going to do well in Chem 1331 and get off to a good start, it is important that you are very familiar with the things that are in this review chapter. And so that's what I'm going to do today, is sort of give you some of the highlights for the review chapter, some of the things that we expect you to, again, know off the bat, and things that we're going to encounter throughout the semester in various contexts, but that we're not going to spend a lot of time teaching necessarily. All right, so here we're going to go, let's get into it. Another thing I'll mention before I start is that there is a review homework assignment in Blackboard that I encourage you to do. It's not required, it's not going to count for a grade of any type, but it is a good way to test yourself and make sure that there are no topics that you're a little bit behind on. And if you are, it's okay, we just need to make sure we address them as soon as possible. So the first thing I want to talk about today are units of measure. So this is a science course. We're going to be dealing with measured quantities, although we're not going to be making measurements ourselves in the lecture course, obviously, but we're going to be doing a lot of problems that involve numerical quantities, physical measurements, and things related to chemistry. So that's not what I meant to do. Hang on. Still need to relearn how to use the technology since it's been a while since I've done this. All right. So what we're going to talk about are units first, and the key concept here is that all measured quantities need units to be meaningful. All right, and you guys can kind of understand this from your everyday life. If you go to the store and ask someone, how much does this cost, and they just say 7, obviously you don't know if that's dollars, cents, or some other unit. So anything you're talking about that's a numerical or measured quantity needs to have a unit attached to it to make that quantity meaningful. Or, if I say, someone asks you, how tall are you, and you say, I'm 75, well, what units are you talking about? And that, again, you need units on there to make that number actually mean anything. So we're going to talk about primarily the standard units, or what are called the SI units of measure. It's like a French system international, or something of that sort. But anyway, these are the sort of typical units that we use in science. You'll see them both in chemistry, physics, pretty much any other science course you use is going to revolve around these units. Now that said, there are other ones that we will come across here and there, so these are not the only units of measure that you'll need to be familiar with, but these are the standard ones, and these are the ones that we will use most often. Okay, so for mass, the standard unit of measure is kilogram. Now we're going to talk on the next slide about what this first part, kilo, means, and the abbreviation for that is kg. In chemistry, we more commonly use grams, without the kilo prefix. Grams is a more common unit of measure in chemistry, but kilogram is technically the standard SI unit, and that's what all the sort of related physical units are going to be based off of. In physics especially, you'll see that. All right, and then the unit of length, which we don't do a lot with length in this course, but there might be a couple things here and there where it comes up, is the meter, abbreviated as M. The standard unit of time is a second, which you likely already know what that is, and is abbreviated with just the letter S. And then temperature, the standard SI unit is called Kelvin. We will also use degrees Celsius a lot, and we're going to talk more about temperature units later on in this discussion. So, but anyway, Kelvin is the standard one, and we will encounter that in many cases in this course. For electric current, the standard SI unit is ampere. You might see this a little bit in Chem 2, so 1332, if you take that course after mine, you will do a little bit with electric current, but in this course we're not really going to deal with that at all. The standard unit for the amount of substance, this is going to be one of the most important concepts, so you don't need to necessarily know what it means now, but just to introduce it, the amount of substance is measured in moles, and then abbreviated with MOL. Probably the world's stupidest abbreviation because they just took off one letter and it's pronounced exactly the same, but nonetheless, that's what we're going to be talking about a lot in Chem 1, and it's going to be a topic that follows you for the rest of your chemistry career. And then luminous intensity. So again, something we're not going to see in here or probably in any chemistry course you take, but it might come up in physics context. Luminous intensity is basically a measure of how bright light is, and the unit for that is called the candela, and it's abbreviated as CD. But again, we're not going to see those. So I will put stars next to the ones that we will encounter quite a bit. So mass, length to a lesser extent, but we will see it at times in this course. Time to not a huge extent, but also comes up here and there. Kelvin is a very important one, and then mole is the most important one on this list, most likely, for us to understand. So we will get to all of these later on, how we use them in chemistry and why they're important in chemistry, but for now you at least want to know what these units are, just so that when we encounter measured quantities that have this units, you'll already be familiar. So there is a perhaps more comprehensive table in table R1, which includes these and probably some other SI units as well, but ones that I have stars next to are the ones you're definitely going to want to know as we get into the course. Now, these units also have prefixes associated with them, or prefixes that can be added. We saw that the kilogram already has it, and so, you know, but then you can really attach prefixes to any unit to modify the size of the unit. So that's really what these prefixes do. They're on table R2, so if you're following along with the textbook, this information comes straight off of that table. And they change the size of a unit in multiples of powers of 10. So they're going to all be multiples of 10 to some power n. Okay. So we have basically some prefixes that make the unit larger, that make the unit, you know, counting more than one, and then we have some that make it smaller, that means it's a fraction of that unit. So this dividing line here is going to be basically the number 1, which would just be the unit itself, and then the prefixes will then modify that in different ways. So the prefixes that make it larger, there are more than this, but I'm going to give you the important ones that you need to know for this course. So mega, which has the symbol capital M, means that you're going to multiply that unit by 10 to the 6th. So if we have 1 megagram, that means we have 10 to the 6th, or 1 million grams. Okay, so that's what that sort of prefix tells you. So it's a it's a numerical prefix that modifies the unit. Another important one, and these this one we will see a lot. So I'm going to put the ones, again, stars next to the ones that we will see the most in this course and that you definitely need to know. Others could come up from time to time, but you definitely want to know kilo is one, because that's, again, it's part of kilogram and it's going to be part of other units that we likely see as well. This has the symbol lowercase k, and it modifies the unit by 1,000. So a kilogram is 1,000 grams. And as I said, grams is very common in chemistry, but kilograms, for whatever reason, is considered the standard SI unit. There's a couple other that refer to measurements that are larger, that modify the unit to make it larger, but we don't see these very much in chemistry. So there's hecto. You've probably heard of a hectacre. I believe that's the same prefix, but we're not going to really use this in chemistry. But that's going to be multiplying by 100, 10 to the second. And then deca, abbreviated with DA, is when the unit is multiplied by 10. So if you have a decameter, that's going to be 10 meters. But again, it's not when we use a lot in chemistry. It's really the only prefix we'll use that's larger that we encounter a lot in chemistry is kilo. I guess I'll put a star next to mega because we might see that at times when we talk about megahertz, the unit of frequency that we'll get to pretty early in the course. But hecto and deca are rarely used. All right, and then if we think about the ones that are smaller than, that make the unit smaller, so you have deci, D-E-C-I, abbreviated with just the letter D, and this means dividing by a factor of 10 or multiplying by 10 to the minus 1. So a decimeter would be 1/10 of a meter, or 10 centimeters. So it's again, the one not the one that we use a lot, but it is out there. Centa is one that we do use a lot because especially the unit centimeter comes up a lot in both chemistry and physics. And so this is abbreviated with just lowercase c, and it means 1/100th. So a centimeter is 1/100th of a meter, or a centiliter, which we don't use a lot, would be 1/100th of a liter, and so on. All right, and then we have milli, M-I-L-L-I, which is lowercase m, and that means 10 to the minus third. We use this one a lot as well. And then really all these smaller ones use a lot because, as we'll start to learn, in chemistry we're dealing with very small particles, atoms, and molecules, so we have to use these smaller units quite a bit in chemistry. So micro is one that will come up from time to time, which it's abbreviated with the Greek letter mu, which I'm terrible at drawing, but we're going to learn a lot of Greek letters this semester, and this is the first one, which is mu. And it means 10 to the minus 6. So if you're talking about a micrometer, or what's sometimes called a micron, that's a very small unit of measure, but it's one that we will see at times. And then one that we will probably see the most in this course, especially early on, is nano. N, which is 10 to the minus 9. So it's, again, a very small measure, but nanometers especially is a unit of wavelength that we will see earlier in the course. So again, don't worry too much about the context of these right now, because we will introduce that as we go through, but these are the units, and when I start using them throughout the course, it'd be very helpful for you to already be familiar with them as I introduce them. All right, now the other thing I want to talk about a little bit is uncertainty in measurement. This is not a terribly important topic for the lecture course. It is something that you will really need to know for the lab. But the key point I want to bring up is that when you make a measurement of any sort of physical quantity, there's always going to be some uncertainty. You can't know exactly what that number is from measuring it. There's always going to be a range of values that it could potentially be, and that's going to depend on how good and how precise the measurement apparatus you're using is. It could depend to some extent on the skills of the person that's making the measurement, and so on. So there's it's an really important topic in scientific research and in laboratory laboratory science especially, but it's not one we're going to really have to deal with a lot in this course, but I do want to make sure you're at least aware of it. So which quantities have uncertainty? Well, that's all of them. So any measured quantity you make is going to have an uncertainty associated with it, and they're going to have certain and uncertain digits associated with them. So certain digits are going to be those which are not estimated. So whenever you make a measurement, there's going to be typically at least one or more digits that you know exactly what they are. There is no uncertainty in them. But then there's always going to be one or more digits that are uncertain, which are digits that must be estimated, or which, based on the precision of the instrument you're using to make the measurement, you cannot precisely know what those are. All right, so that's kind of the idea about uncertainty, and I don't want to say anything more about it because it's not something that's going to come up really in the course. But what uncertainty then sort of leads us to is this concept of significant figures. And we do not make a big deal about significant figures in the lecture portion of Chem 1331. I'll be upfront about that and say that there's not really going to be any direct test questions or homework questions dealing with significant figures, or we're not going to count you wrong on a test if you have the wrong number of significant figures. That's just not something we do in this course. But what I will say is you're going to need to understand significant figures for the laboratory portion of the course. That's going to be something that's very important for what you do there, which I don't teach that part of it, but you will likely have to take it this semester or in the near future. And then also if if you're going to go and do experimental research of any type, you need to understand significant figures very well for that. And I do believe, although I haven't taught this course, so I'm not 100% sure if it's still the case, that in Chem 1332, which is the follow-up to this course that most of you will take, in Chem 1332 they do make a little bit bigger deal about significant digits and make sure that you report answers correctly with the proper significant digits in the right format and all that. So let's talk a little bit about the rules for these, and like we said, we're not going to use them a lot, but I think it's important to at least mention. Okay, so when we have a measured quantity, we're going to have, we report the number, we're going to have all of the certain digits. So as I said, when you make a measurement, some of the digits are going to be certain. They're going to be ones that you know 100% what they are. And then there's always going to be one uncertain digit, and all of those digits combined are considered significant. So if you look at a measured quantity, you can determine how many significant digits there is based on how the number is reported. So if we have non-zero digits, all non-zero digits are going to be significant. All right, so as an example, if our measured quantity is 123.4, with obviously some units associated with it that I'm leaving out, this number would have 4 significant figures because, which I'll abbreviate as sig figs, it would have 4 significant figures because there are 4 non-zero digits in the number, and that's all there are. Now, when we have zeros in the number, they have some different rules associated with them. So leading zeros, as they're called, these are going to be zeros coming before the first non-zero digit. So all zeros that are coming before the first non-zero digit, all of these are going to be non-significant. All right, so if we have this number here as an example, 0.0001234, these zeros that come before the first non-zero digit, so the first non-zero digit is the 1, there's 4 zeros before that, all of those are non-significant. And the reason is that those leading zeros that come before the first non-zero digit are just telling you the order of magnitude, or the the scale of the number, which, so in many cases, it's better to write this in scientific notation, 1.234 times 10 to the minus 4. And if we do that, it very clearly has 4 non-zero significant digits, okay? So for large, or for very large, very small numbers, it's actually in many cases helpful to write them in scientific notation before determining how many significant digits there are. Now, if we have captive zeros, we have another type of zeros called captive zeros. These are zeros that are in between non-zero digits, and these are going to be significant. All right, so they're not leading zeros. They don't come before the first non-zero digit. They're called captive because they're captured in between non-zero digits, and these are going to be significant. So as an example, if we have this number here, 1203.004, we want to know how many significant figures does this have. All right, so if we were to count the significant digits in this number here, we have some zeros in there, but they're all in between non-zero digits. So this 0 is in between the 2 and the 3. These 2 zeros are in between the 3 and the 4. So these are all captive zeros, which means we count all of them as significant digits. So this number has 1, 2, 3, 4, 5, 6, 7 total significant figures. I guess we use significant digits and significant figures sort of interchangeably, if that was not clear already. And then trailing zeros, these are the ones that are a little bit weird to deal with, and so we want to make sure that we're as clear as possible when we report numbers. So these are zeros at the end of a number. And the one time when they are definitely significant is if they come after a decimal place. So if the number has a decimal point, any trailing zeros, which are zeros at the end of that number, are going to be significant, okay? So if we have some examples here to sort of highlight some of the different possibilities. If we have the number 0.123400, this has a leading zero, so that's not going to be significant because that comes before the first non-zero digit. But we have 2 trailing zeros that are after the decimal point. And so trailing zeros that are after the decimal point are significant, so we have 1, 2, 3, 4, 5, 6 total in this number. But then if we have the number 12340, 12,340, this one is a little bit ambiguous. So, without a decimal place written, is this number going to be, this last zero here, significant or not? And so this one, typically the rule would be that this has 4 sig figs, that because there's no decimal point in this number, we would assume this last zero is non-significant. But then if we write it, in some cases you'll see it written as 12,340 with a dot, a decimal point after it. In this case, we would treat the 0 as significant and say that this has 5 sig figs. So these trailing zeros at the end of non-decimal numbers can be a little bit confusing at times. Again, we're not going to make this a huge point of emphasis in this class, but for these types of numbers, it is in general better to write in scientific notation, which removes any ambiguity about which decimals or which digits are or are not significant. All right, so if you write these in scientific notation, then that's going to be clear because all the digits would be part of a decimal number, and you can tell whether the the 0 comes after the decimal point or is not there at all. But at the same time, if you write the numbers in this way, without the decimal point, it's a little bit ambiguous whether that 0 is significant or not, although typically we say it is not significant. If you write it with the decimal point, then you definitely count it. So a little bit of weirdness with trailing zeros, but again, that's something that we're going to have to worry about too much in this class. Now, there are some numbers that we call exact numbers that are assumed to have infinite significant figures. So any measured quantity, anything that we use that we make a measurement on, is going to have a certain number of significant digits associated with it, which is determined by how exactly we make the measurement, how precise the instrumentation is that we use to measure it. But there are some quantities that we're still going to use that are assumed to have infinite significant figures because they are not measured quantities. So if we have counted quantities, so if we say that we did 10 experiments, so these are, or if we have 5 beakers in the lab, or if we count 11 atoms, etc. So anytime we're doing counting to determine how many things there are, those are going to be called counting numbers, and they have infinite significant figures because, if we count something and it's counted one at a time, we know exactly how many of those we have. There's no uncertainty in how many we have if we're doing counting as our way of measuring. All right, and then if we have numbers in calculations, in formulas basically. So if we have the formula for the area of a circle, which is 4 pi r squared, that would be the surface area of a sphere. But anyway, if we have an equation like this, 4 pi r squared, r would be in reality a measured quantity, but then this part here, which I'll highlight in the formula, the 4 pi part, that's going to be, those are exact numbers. So anytime you have a physical constant like pi, or many other physical constants that we'll use in this course, if you have that as part of a calculation, and you're not measuring that number yourself, but you're just using it to calculate something else based on a measured quantity, those exact numbers have infinite significant figures. So really the significant digits are only going to be determined by the value of r that you have here. And then if we have conversion factors, we're going to use conversion factors a lot in this class, which are factors that allow us to convert between two different units. And these are, again, just based on definitions. They're not really measured quantities. So, 1 inch is equal to 2.54 centimeters. 60 seconds is 1 minute, as we know. Or 10 to the third meters is 1 kilometer. Anytime we're using numbers like this, which are just unit conversions and are based on the definition of that unit, then those are, again, assumed to have infinite significant figures. And so that's sort of, anytime you have an exact number, there's these sort of 3 categories of exact numbers that I've listed here. They all assume infinite significant figures, and that's how we're going to treat them. All right. So the only numbers where you have to worry about significant figures are going to be ones that are measured quantities. All 3 of these, counted numbers, numbers that are just part of formulas for calculations, and conversion factors and other definitions that are based on just the unit itself, those are going to be infinite significant figures. Now, why this is important to know is that, why are significant figures even necessary to even think about, is because what we're usually going to do in scientific, in any sort of scientific context, in chemistry in particular, is we would take, 2 or more measured quantities in many cases, and then use those measured quantities to calculate something else about the system that we're studying. And so you have to do basically mathematical operations that involve measured quantities, multiplication, division, addition, subtraction, and so on. And we then, the answer that we get out of that, the sort of the result of that mathematical operation, we need to know how many significant digits did that have, because we can't calculate a number that's more precise than the measurements that it's based on. And so we use these rules to make sure that whatever we calculate from measured quantities has the correct precision, the correct number of significant digits based on the numbers that were used to determine it. Okay? So again, not so important in this course, but important for the lab and for really anything you do during your scientific career. So if we're doing multiplication and division on measured quantities, the rule for this is actually quite simple. the answer that we're going to report is going to have the same number of significant figures as the number in the calculation that has the fewest number of significant figures. All right. So we're going to multiply and or divide two or more numbers, and we're going to figure out, okay, which of those two or more numbers that we're multiplying and dividing has the least number of significant figures, and then our answer should have that same number of significant figures, okay? So as an example, if we do this calculation here, 12.3 times 2.002, again, these would both be measured quantities with units, but we're just going to go over the numerical part of this for now. And then when we multiply these together, if we just put the numbers into our calculator, what we get is 24.6246. But we have to figure out what should we actually round this answer to have the correct number of significant figures. So if we look at the two numbers we multiplied to get that result, 12.3 has 3 significant figures, 2.002 has 4. Remember, these captive zeros are significant, so all 4 of these are significant. And so our product then should also have 3 significant figures, because that's the least number of significant figures in the two numbers we multiplied. So we're going to have to round this to 3 significant figures. So it's going to be just the first 3, 24.6 would be the way we would report the answer, 2 to 3 significant figures. Okay. We also have to worry about a little bit about rules for rounding. Typically, if it's 5 and above, you round up. If it's 4 and below, you round down. Sometimes people use different rules for 5, but this one, the digit after the third significant figure is a 2, so we round down, we keep the 6 there, we don't round this to anything else. All right, and then for addition and subtraction, the rules are a little bit more complicated in some sense. So it's not based on significant figures in the numbers that we're adding and subtracting, but it's going to be based on the number of decimal places. So it's going to have the same number of decimal places as the number in the calculation that has the fewest number of decimal places. So it's not based on total number of significant figures, it's just based on decimal places. Another important thing about adding and subtracting, which we want to make sure we remember if we ever have to do it, is that we can only add and subtract numbers that have the same units. So multiplying and dividing, you can multiply and divide numbers with, any random units associated with them. But when you're doing addition and subtraction, the two numbers need to be in the same units first. And then the way you report the answer is to have the same number of decimal places as the number that had the fewest decimal places that you're adding or subtracting. So if we want to add 12.3 and then 2.002, we multiplied those two numbers earlier. Now we don't have to, if we're adding them, we don't have to worry about the number of significant figures. We just need to make sure that the two numbers are in the same units, which I'm not specifying here, but they would need to be before we added them. And then we just look at decimal places. So this clearly has 1 decimal place, 0.3. This one has 3 decimal places, 0.002 after the decimal. And so when we add these together, we get 14.3002, but we need to round it to only 1 decimal place because this number here, 12.3, only has 1 decimal place. All right, so we're going to round this off, and it would be reported as 14.3 with just 1 decimal place. All right. So I just spent a lot of time going over rules for significant figures, even though I said they're not that important in this class. I still stand by that, but at the same time, it's very important for all aspects of science. All of you guys are going to likely be taking more science courses than just this one. So even if we don't use it in Chem 1331, it's good to always remind ourselves of these rules because they're very important in all of experimental science. All right, so let's move on then to some more information about mathematical combinations of measured quantities. In particular, dividing or multiplying things together is what we're going to really focus on here. So we talked about the rules for significant figures for multiplication and division, and then what happens to the units when we multiply and divide two quantities. So when we multiply or divide two measured quantities, the associated units are also multiplied or divided. Okay. So whatever we do to the numbers are going to be also carried forward with the units themselves. And that often then results in compound units that have more than one unit associated with them. Okay. So for example, if we wanted to determine the area of a standard piece of paper, 8.5 by 11 notebook paper, remember the area, we just multiply the lengths of the two sides. So if we have 8.5 inches on one side and 11 inches on the other, we would multiply the two numbers together, 8.5 inches multiplied by 11 inches. Numerically, that comes out to 94 with two significant figures in both of them, so we'll keep this as 94. But then for the units, we have inches on each of them, so we're going to multiply inches times inches, and then we would write this measured quantity as 94 square inches, or inches squared, okay? So this is how we would report this number, where again, we multiply the two numbers and we multiply the two units, inches times inches, okay? So let's say we wanted to do speed calculation, not in chemistry, of course, but we would do this in physics, and this is something you're probably already familiar with. So let's say we're driving to Galveston for a fun weekend party of some sort, and we want to travel 51 miles to Galveston, which is about the distance from here. And let's say we want to do it in 45 minutes, 3/4 of an hour. All right, now that's making pretty good time, but possible if there's not too much traffic. So if we want to calculate the speed that this would require, or the speed that this corresponds to, again, speed is distance divided by time. We're going to see maybe a little bit about speeds later on in the course, but it's not a very important concept in chemistry. But from the standpoint of how the units work, if we divide distance by time, our distance here is 51 miles. The time unit I gave you was 0.75 hours. And so then when we divide the two by each other, the numerical answer is 68, and then the units that we get are going to be just the two units divided by each other. Miles divided by hour, or miles per hour, as we call it in American lexicon. All right, so it's going to be miles per hour, and so again, the two units are just divided as well. So we're going to be doing a lot of this in this course of taking measured quantities and multiplying and dividing them. It is important to recognize that the units are going to be also multiplied and divided in the same way. Now, as I already sort of mentioned on the previous slide, when we do addition and subtraction, the two quantities that you're adding and subtracting have to have the same units, and then the units of the answer will also be the same. So in addition and subtraction operations, we don't change the units at all. We make sure that the two numbers have the same units before we add and subtract them, and then the answer that you get would also have those same units. All right, so it's not possible to add two numbers that have two different units. And if that's confusing to you, think about how you add up money, right? If you have $1 and you add 50 cents to that, you don't just add 1 plus 50 and say I have $51. That would be nice, but that's not how it works. If you have $1.50, you have to put them in the same units before you add them together, and then you'd figure out that that's $1.50, not 1 plus 50. Okay, so sometimes for measured quantities, it's helpful to think of money, because a lot of the stuff we do with money has really the same principles associated with it as measured scientific quantities. All right. The next topic I want to move into, which is exceedingly important for this course, and it's going to be one that I'm going to harp on over and over again. Let's see how much, geez, a lot left. But one that's going to be very important for this course, one that I'm going to go over time and time again in many contexts, is going to be dimensional analysis, unit factors, unit conversions, a lot of different terminology associated with it. But basically, it's the idea of using equivalent quantities to convert between one unit and another. And as we'll see in this course, sometimes it's two units that refer to the same thing, like 2 units of length, and just converting one unit to another, like inches to centimeters, like we'll do an example of today. But then sometimes it's also equivalent quantities that are actually really 2 different units, but that are equivalent or related to each other in some way that allows us to convert between them. So we're going to use this approach a lot in this course, so I want to introduce the basics of it now. So a unit factor is a ratio of 2 quantities that are equivalent to each other. So basically the ratio equals 1. But it's a ratio of 2 equivalent quantities, and what they're used for is to convert from one unit to another. All right, so why did I say these equal 1? Well, think about it this way. If you're, if you're taking, let's say, 2.54 centimeters equals 1 inch, right? So that's, this is sort of the relationship between centimeters and inches. If we divide both sides by 2.54 centimeters, divided by 2.54 centimeters is just 1, and that's going to equal 1 inch divided by 2.54 centimeters. So this ratio here, 1 inch over 2.54 centimeters, would be called a unit factor. It's two equivalent quantities written as a ratio, 1 inch on the top, 2.54 centimeters on the bottom. We could also write this as 2.54 centimeters divided by 1 inch. So unit ratios, unit factors can be written in both ways, and they're both equally valid. Okay, so when you write quantities in this way, you can then convert between inches and centimeters. There's other ones which you should know. We're gonna, if in a lot of cases we'll give these to you. We're gonna introduce some more throughout the semester. But ones that you should know right off the bat, right off the top of your head, are gonna be the one that I just gave you. We don't do a ton with inches and centimeters in this class, but it's common enough that you should know it. But then other, the common time units we'll see at times are going to be, 60 seconds in 1 minute, 60 minutes in 1 hour, written either direction, obviously. Those you should obviously know, and you probably already do. And then any of the ones that involve prefixes, you should be able to also formulate a unit conversion factor involving those, right? So if we have, for example, 10 to the third joules unit of energy in 1 kilojoule, that's going to be a conversion we'll use a lot. And that one we're not going to give to you because it uses the prefix kilo, which means 10 to the third, as I introduced earlier. Or similarly, if we want to do a measure in millimeters, that's going to be 10 to the minus third meters. This can be written in either way, so you can either write it as 1 millimeter is 10 to the minus third meters, or you can write it as 10 to the third millimeters per 1 meter. I tend to prefer avoiding negative exponents, so I would more likely write it like this here, 10 to the third millimeters per 1 meter, but they're equivalent, you can do it either way. And then the one that we'll use a lot early on in the course is 10 to the 9th nanometers per 1 meter. Okay? So there's a lot of these that are going to involve prefixes, which you should know those. You should be able to formulate unit conversion factors without having to, have us give them to you or having to look them up or anything like that. These should be ones that you're able to, get right off the top of your head. All right, so I'm going to take a quick pause here, and I'll come back with the rest of this later on. All right, resuming now after a break for a meeting. So we are going to do a couple example problems related to the concepts we just talked about of using unit conversion factors. So as an example, first one, Professor Tietz lives 25 miles from UH. What is the distance in feet? So yes, it's true, like many of you, I have a pretty terrible commute, but not really the purpose of this problem. The purpose is to understand how to convert that into a different unit of measure. And so the way we're going to want to do this is, if we're looking for the distance in feet, we would start with the given quantity. So this is going to be an approach that I want to start developing for you now that we're going to use over and over again in this course. We start with what we're given, which is the quantity 25 miles. And then we're going to write the unit conversion factor, 1 mile equals 5,280 feet, in such a way as to convert from miles to feet. And the way that we're going to do that then is we want to make sure that miles cancel out. So we want miles in the denominator, and we want feet to be the unit that we convert into. So we're going to write the unit factor in this way, which means we're going to put 5,280 feet in the numerator over 1 mile in the denominator. That means that the units miles cancel out, and we go from miles to feet by multiplying those together. And we're going to get, if we do it in scientific notation with the correct number of significant figures, 1.3 times 10 to the 5th feet. All right, so basically 130,000 feet that I'd have to drive every day to get to work to experience the joy of teaching chemistry. All right, so that's going to be how we do those, and that's just a simple one-step problem. Now we can also do multiple steps for unit conversion. So sometimes we don't have a simple conversion factor to get from one unit to another. At least we don't have one that we necessarily know right off the top of our head, so we have to sort of use a combination of two or more conversion factors, and that's what this next one's going to be. So we're going to do the same distance, but now we want to convert it into meters. And I don't know, and I didn't give you one here, what is the conversion to go from miles to meters? I mean, there would be a number that you could come up with, but it's not given here. It's not a very common one. So we're going to do this in multiple steps. So, there's often many ways you could approach the problem, but one way to do it is we want the distance in meters. We're starting with 25 miles as the given distance again. And if we want to go from miles to meters, we just have to take it forward using the steps that we do know. So we have a conversion factor from the previous problem that takes miles into feet. So we're going to do the same step at the beginning. So 5,280 feet per 1 mile. So same identical first step. But now our units is now feet. We want to go into meters. We don't have a conversion factor here that goes from feet to meters directly, but we have one that goes from feet to inches, which we likely already know, even though it's given here as well. So we're going to do 12 inches in 1 foot. That ensures that the units feet cancel out, and we're in inches now. We don't have inches to meters either, but we have inches to centimeters, which we've also talked about earlier. So we're going to do inches in the denominator, centimeters in the numerator, so 2.54 centimeters in 1 inch. And then the last step, now that we're in centimeters, I didn't give you the conversion to meters, but this one we should know because centa is one of those common prefixes, which means 1/100th. And so we can then convert to meters. If we want meters in the numerator, centimeters in the denominator to cancel out, there's a couple ways we can write this. But we would do 1 meter is 100 centimeters, or alternatively 10 to the minus 2 meters is 1 centimeter. So we could have inverted this ratio, wrote it in the other way, but that it would give us the same number either way. So centimeters now cancels out, and we're in meters, which is the unit that we want. So when we're doing unit conversions, we basically just have to do as many steps as it takes to get from the unit we start with, in this case 25 miles, to the unit we're trying to solve for, which is meters. And if you can't do it in one step, you can do it in multiple steps. Here it was about 4 steps, as it turns out, but that gets us into the correct units. I'm just going to have to multiply all these numbers and divide, and what we get is 4.0, assuming I did the math right, 4.0 times 10 to the 4th meters, and that sounds about right. Okay, and we're going to use that approach a lot in chemistry, not necessarily just for converting distance units. That's not something we really have to do a lot, but for other types of chemistry problems and other types of units that are more relevant to chemistry, this is going to be a very common approach. All right, and then one other unit conversion that I'll go through is if we have a compound unit now. So the previous ones were just the unit of length, meters and miles and things of that sort. Now we're doing a compound unit conversion. So let's say we're driving 65 miles an hour on the freeway, and we want to figure out what's that in meters per second. And again, I gave you some of the distance conversion factors here to help you out. So again, we want to look for the speed or the velocity in meters per second. And we're starting with a speed of 65 miles per hour. And we can write that then as a ratio of 65 miles over 1 hour. So that's what mph means, miles per hour. You can write it as 65 miles in every 1 hour. And then what we want to be able to do then is to get this into meters per second, we need to convert miles into meters, which we just did in the last slide in a few steps. So we want this to be converted into meters, and we want the time to be converted into seconds, and that would give us then meters per second. So we can do that in either order. So if we want to convert the numerator into meters, we're going to follow the same set of steps as last time. We're going to do miles into feet using that conversion factor that we've already dealt with a couple times. Feet into inches. And inches into centimeters. And then centimeters into meters. So these first 4 steps are identical to what we did last time. We're just starting with a different quantity initially. So now we have converted miles into meters, so we're all set on the numerator, but then we also have to convert the meters into, the hours in the denominator into seconds. And so what we do for that then is, let's write this as an intermediate. So the current units that we have, we've canceled out all these. We have meters over hours right now. So just write that out to remind ourselves where we are. And then to convert hours into seconds, we're going to do, again, a two-step conversion. So we want hours to cancel, and we'll first go into minutes. So we're going to have 1 hour is 60 minutes, and that means hours cancel. Now we're in meters per minute, and then minutes into seconds. We want minutes to cancel, so it goes in the numerator to cancel with the minutes in the denominator. Seconds in the denominator, so that's going to be 1 minute is 60 seconds. So we're going to basically divide by 60 twice to convert hours into seconds. And so when we work all this out, what we should get is 29 meters per second. All right, so it's really the same approach. It's just recognizing that when we have compound units, which is a ratio of 2 or more units, in this case just 2 miles over hours, we convert the two separately from each other to get to the final compound unit that we want. All right. Another quantity, another unit of measure that we need to talk about is temperature. Now, we said earlier that the standard unit, or the SI unit for temperature, is Kelvin, but we're going to use some other ones in this course, and there's some other ones that are common in everyday life that we want to be familiar with and know how to convert between. So, first of all, what is temperature a measure of? This is going to be something that we deal with more directly, probably in the second half of the course more than the first half. We're talking about really what does temperature refer to in terms of the behavior of molecules, but it's a measure of heat content. So it tells you how hot or cold something is, and we will deal with a lot in this course of what does this mean at the molecular level, what are happening to the atoms and molecules as a function of temperature, but that's much later on. But as we know already, probably from everyday life, temperature is a measure of how hot or cold something is. That's how we talk about the weather. It's how we talk about cooking temperatures. All those different things are a measure of heat content. So there are 3 common temperature units. The one that we will use probably the most in this class is Celsius. And I really wish that the United States would get its act together and just use Celsius for everyday life temperature reporting, but we don't. But Celsius is what we typically use in science. So it's degrees C, and it's a pretty convenient unit because the freezing point and the boiling point of water are very nice round numbers. So the freezing point of water is 0 degrees Celsius, and the boiling point of water is 100 degrees Celsius. Those freezing points and boiling points of water you should know in that unit specifically. And the relative size of 1 degree, I'll call 1 here. So 1 degree Celsius is how we're sort of going to standardize to. If we go to Kelvin, which is the SI unit, and we will have to use Kelvin as well, it depends on the context whether you need Celsius, Kelvin, or whether it matters. But we will use Kelvin a lot, and actually it's never wrong to use Kelvin in a chemistry context. And Kelvin is actually the same degree as Celsius, so it's the same interval, same size for each individual degree, but it's just shifted by 273.15. All right, so the freezing point of water in Kelvin is 273.15. The boiling point of water is 373.15. So what you'll notice is that there's 100 degrees in between the freezing and the boiling point of water. So the relative size of a Kelvin degree is the same. It's just that the scale is shifted. And Kelvin is basically set up so that it is impossible to have negative temperatures. In Celsius and in Fahrenheit, which we'll get to here in a second, you can have temperatures below 0. We don't experience those too often in Houston, but they do occur, and they can be accessed in artificial settings for sure. Kelvin, the absolute smallest temperature you can get is 0, and so the whole scale is shifted relative to the other two, but the size of the degree for Kelvin and Celsius, the size of 1 unit, is the same. Now, Fahrenheit is the weird one that we still use in the United States, which I've been disappointed about for my whole life, but it doesn't seem to be changing anytime soon. So it's going to be abbreviated as degrees Fahrenheit, degree F. And as you probably know, because you've dealt with this for most of your lives if you've lived in the United States, is that the freezing point of water is 32 Fahrenheit, the boiling point of water is 212. Fahrenheit's a pretty convenient unit for weather. I mean, it turns out that the talking about the weather in terms of Fahrenheit is a pretty convenient way to do it, but it's not very convenient for anything else because it's just not based on anything very simple from a scientific standpoint. Now, the size of a Fahrenheit degree is smaller. It's 5/9 the size of a Celsius or Kelvin degree, so it's actually in some sense a more precise scale because 1 degree Fahrenheit is a smaller unit of temperature. But again, it's not one that we're going to see a lot in this course, but we do want you to know how to convert from Fahrenheit to the other 2 units. So to do the conversions, Celsius to Kelvin is very simple. So the temperature in Kelvin is going to be the temperature in degrees Celsius plus 273.15. So as I said, the 2 scales are just shifted by this amount. And so they have the same degree size but a different 0 point, and that's why we have this conversion. If you want to go from Celsius to Fahrenheit or Fahrenheit to Celsius, this is where things are a little bit weird. So the temperature in Fahrenheit, if we're starting in Celsius, we're going to take the Celsius temperature and we're going to multiply it by 9 degrees Fahrenheit for every 5 degrees Celsius, because as I said, the size of the degrees is different, but they also have different 0 points, different origins, if you will, so we have to add then 32 to that. So the temperature from Fahrenheit, to go from Celsius to Fahrenheit, you take the Celsius temperature, you multiply by 9/5, and then you add 32. Now we're not often going to do that because usually we don't want the temperature in Fahrenheit because none of the chemical equations we're going to use are going to involve Fahrenheit temperatures, but that's how you would do it. And then if we want to go the other direction and just undo that, the temperatures in degrees Celsius is going to be, you multiply by 5/9, and you take this difference here. So you take the Fahrenheit temperature and you subtract 32. So it's sort of the opposite of the above one. You start with the Fahrenheit temperature, subtract 32, and then multiply by 5/9. And the reason these are so complicated is because you have a different degree size for these units. So Celsius and Fahrenheit have different degree sizes as we talked about. And they have different 0 points. So they're also phase shifted relative to each other, where 0 Celsius is not equal to 0 Fahrenheit. It's equal to 32 Fahrenheit. So converting between these is complicated. We won't have you do it very much, but I would, it does behoove you to know how to do it because it might come up here and there on a homework assignment. I think we kind of leave it off of tests, but don't quote me on that. All right, so as an example, if we want to go from, we have minus 23.6 degrees Celsius, and we want to convert it to Kelvin and Fahrenheit. As I said, converting to Fahrenheit is not a very useful thing to do, but we're just going to do it for the sake of exercise. Now, Kelvin is very easy, and this you have to be able to do in this course very well, because in some of the chapters later on with gas laws and what we call thermochemistry, stuff we'll get to much later, you have to do this. So 273, we're going to add 273 to this to get from Celsius to Kelvin. So we get 249.6 Kelvin. Technically speaking, it's 273.15, but as we said, if you just do 273, that'll get you close enough. And then to go to Fahrenheit, it's the more complicated one, as we said, where we're going to take minus 23.6 degrees Celsius. We're going to multiply it by the factor that converts the size of the degree, 9 degrees Fahrenheit over 5 degrees Celsius. And then we're going to add to that 32 degrees Fahrenheit to shift the scale. And so when we do this, we get minus 10.5 degrees Fahrenheit. So these are both very cold temperatures in terms of what you'd experience on planet Earth, but I have experienced them before when I lived up north. So anyway, that's how you would convert between these. It's not a particularly useful thing we'll have to do in chemistry because we don't use Fahrenheit in chemistry, but that's how it would work. Okay, the last concept that I want to go over, I think it's the last concept, yes, is density. So density is something that is fairly important in chemistry. It's certainly a concept that we will see from time to time. And its definition, and this is something that you likely learned in high school and will probably also see potentially in physics courses in addition to chemistry, but it's a ratio quantity. So it's the mass of a substance per unit volume. All right, so it's that's sort of what the definition of density is a ratio of mass to volume. And why is it important? So one reason it's important is that it's what we call an intrinsic property. It's a property that doesn't depend on how much substance you have. So if you have 1 drop of water or if you have a lake of water, the density of that water will be the same because there's a ratio of mass to volume. So it's what we call an intrinsic property. It doesn't depend on how much substance you have. And then each substance has a characteristic density. Now, it's not sufficient to necessarily just use density to identify a substance, but it's a quick way to help you identify whether a substance is correct or not. So in real life, this is actually used a lot in determining whether someone's trying to sell you fake gold. So pure gold has a very characteristic density value. It's very easy to measure because all you have to do is measure the mass and volume, which are two very simple, non-destructive quantities to measure. And you can use it to identify if someone's trying to sell you real gold or fake gold, because real gold will have a certain density. People that try to sell you fake gold, that density will be at least a little bit different from the density of real gold because it's a different substance and has a different density. So it's not the only analysis you should do in that situation, but it's a very quick and easy one to determine whether the substance is what you think it is. Another reason, which I'm showing here in this picture on the right, is that it can also be used to separate mixtures of liquids. So if you have liquids that don't mix with each other and have different densities, like oil and water is probably the common one you're familiar with, if they have different densities, they will separate into different layers, and then you can easily separate the liquids from each other based on their density. So it's useful in chemistry, and it's not one we will have a lot of explicit problems dealing with in Chem 1331, but it will be a concept that comes up from time to time in sort of a larger scope of things that we're dealing with. So in density, there are a few, as I said, it's a compound unit of mass per volume. Usually in chemistry, the volume unit that we're using is cubic centimeters. So it's going to be usually grams per cubic centimeters is the most common unit we'll deal with for density. That's sort of the common way of reporting it for solids. But keep in mind that 1 cubic centimeter is equal to 1 milliliter, which is more often what you use for liquids and gases. But the size of those units is exactly the same. So 1 gram per cubic centimeter is exactly equal to 1 gram per milliliter. There's no difference between a cubic centimeter and a milliliter. It's just two different ways of writing the same volume unit. And there's one substance which the density is, you should know off the top of your head and not have to look up or have us give it to you, and that's water. And it's very easy to remember because the density of water is 1 gram per milliliter, which can also be written as 1 gram per cubic centimeter, as I said. So the density of water is 1 in those units, and you should know that because there are going to be problems later in the course where you have to use the density of water, but it's just 1, so it's very simple to deal with. All right, so let's talk about a little bit how to calculate density. So in this sample problem here, we have an empty container that weighs 86.35 grams. When we fill it with water, it weighs 161.61 grams. When the unknown liquid is added and the mass is filled, the container weighs 151.60 grams. What is the density of the unknown liquids? This is actually going to be a two-step problem. So when we're doing sort of complex problems like this one's not too bad, but it has a few steps involved. The first thing I like to start with is, what are we looking for? We're looking for the density of the unknown liquid, and so for that we need the mass of the unknown liquid and we need its volume. Okay? And so once we have those two quantities, we are going to be able to, we're going to be able to change, divide the two and get the density. So once we have both of them, we're just going to do the division and we're all set. So, but neither of these are given to us directly. We didn't tell you exactly how much unknown liquid we have because we told you that the mass of the filled container is 151.60 grams, but that includes the liquid and the container. So if we want to find the mass of the unknown liquid, we have to subtract those two, all right? So it's 151.60 grams is the mass of the filled container. And then we told you in the first sentence that the empty container is 86.35 grams, so the difference between those will give you the mass of just the liquid itself. And so when we subtract those two, we get 65.25 grams. So that's the mass of unknown liquid that we're using in this hypothetical experiment. Then we have to divide that by the volume of the container. Now the volume of the container is also not directly given to us, but for that we are going to use the information in the first sentence about how much it weighs with water in it. So when we fill this container with water, the mass of water that it holds is going to be, by the same argument, the mass of the filled container with water in it, 161.61, and we're going to subtract from that, again, the mass of the empty container. And so this container will, when filled up with water, has 75.26 grams of water. And so if we want to know the volume of the container, we're going to use the density of water. So we have 75.26 grams of water in this container, and the density of water is 1 gram per milliliter. So we want grams of water to cancel and then convert into milliliters, and that's just 1 over 1 because the density of water is 1 gram per milliliter. So we're basically dividing by the density, if you will, but it's just 1, and that converts grams into milliliters. So it's a helpful shortcut to remember that if you have a certain mass of pure water in grams, you have the same number of milliliters. So 75.26 grams of water has a volume of 75.26 milliliters. So that's the volume of our container, and so we're going to divide that, put that in the denominator up here to get the density of the unknown, which is the mass of the unknown liquid divided by the volume of the container, which comes out to 0.8670 grams per milliliter if we're using the proper number of significant figures. Okay. All right, and then the last thing we'll do is using density as a conversion factor, which we sort of did up here. So in this last step here, to find the volume of the container, we use the density to convert between mass and volume of water. And we're going to do the same thing here, but with a different substance, gold. So gold has a density of 19.32 grams per cubic centimeter, and as I said before, this is often used to help identify whether a sample of gold is pure or not, because if it's not pure gold, the density will be something different from that. For example, fool's gold, which you guys might have seen before, which is it's called pyrite, an iron sulfur compound, has a density much less than 19.32. So, even though they look very similar, fool's gold and real gold are very easy to distinguish based on their density. So that's a stupid aside. But here we have gold has a density of 19.32. We want to know how many cubic inches does a standard 12.4 kilogram gold bar occupy. So this is going to be, again, another complex conversion that involves a few steps here. What we're looking for is the volume in cubic inches, so we're going to write that out as what we're looking for, and then we're going to start with what we're given. So we're told that the mass of the gold bar is 12.4 kilograms. So we always want to start with a measured quantity, not with a conversion factor. We're going to use a conversion factor later on. So 12.4 kilograms is the measured quantity of gold that we have in this gold bar, and we want to know what's the volume of that. So the first thing we're going to do is we notice that the density is in grams per cubic centimeter, so we have to convert kilograms to grams first. So we want grams in the numerator, kilograms in the denominator so that it cancels out, and that's going to be 1,000 grams per kilogram. Remember that kilo, lowercase k means 1,000. Okay, so that's going to cancel out. And then what we have is grams of gold we can convert into volume by using the density. So here's the key step of using the density as a conversion factor, which we did in the previous problem. So we want grams of gold to cancel, and we want cubic centimeters to be the unit we get into. And so what we're going to see is that we want grams in the denominator, so the density is 19.32 grams of gold per 1 cubic centimeter. So that's going to be the way we write this. We're actually going to invert this to make sure that grams cancel out and we get to cubic centimeters. And then finally we have to go from cubic centimeters to cubic inches. The way that we do this is we know that 1 inch is 2.54 cubic centimeters. Sorry, 2.54 centimeters. I misspoke there. So 1 inch is 2.54 centimeters, but we want centimeters cubed to cancel out, and we want inches cubed to be the unit we get to, so we have to cube this whole thing. So basically we have to do this conversion, 1 inch over 2.54 centimeters 3 times, because that's going to get us from cubic centimeters to cubic inches. All right, so whenever we're dealing with compound units for area or volume, which are square or cubed, in this case cubic centimeters, we have to use that same conversion factor 3 times to account for the compound nature of that unit. All right, so anyway, when we multiply all the numbers across, what we get is 39.2 cubic inches. Okay, So that would be the volume in a sort of weird unit for 1 gold bar. All right, so I think that takes me to the end of what I wanted to cover today for the reviews chapter. This was not intended to be comprehensive, but I think it does get the most important parts of the review chapter, a little bit of an overview on those. If you have any questions about this, please come to me right away and get them answered, because this is something that we need you to know right off the bat so we can start using these concepts as we go through and learn more complex things in this course. All right, so thank you for tuning in, and I'll see you guys in class sometime soon.